following is a paid advertisement for FutureTech Industries.
Oh hi, didn't notice you there. I'm 59321's Brad Colpers. I'm here to tell you today about an offer not yet available in stores. But Brad, you say, how can you sell something that's only just been theoretically proven? Well, to you naysayers, I tell you we can and we do. Over the next few minutes, we'll introduce you to our new DNA-detecting personal glucose meter. We'll meet the product and materials experts, see our crack team of researchers in the lab, and lastly visit with you, the consumer, to see what the word on the street is about this fantastic new product. Hey, Skip.
Hey, Brad.
What are you working on?
Well, I was just thinking about how far modern technology has come in this past decade. And I was thinking, how difficult would it be to do regular DNA testing in a home setting?
It's quite a problem you got there.
Yeah, but you know, with all this technology, things are just getting simpler and simpler. And we even have PGMs, personal glucose meters, where people, diabetics, can do and test for their sugar levels. And I was thinking, why can't we take it another step forward?
Do you mean like this?
Yeah, exactly like this.
Thank you.
Well, here at FutureTech, for literally days, we've developed the new DNA detecting glucose meter.
Interesting stuff, Jason. But how does someone actually go about developing something this radical?
Here in FutureTech, we have some of the best materials, best design experts, and some of the best people known to man. These people are known as scientists.
Hi, and welcome to the Materials and Experimental Design Division of FutureTech, where we are on the cutting edge of science and technology every single day. And last week was no different when our lead scientist approached me and told me we had to make a glucose meter capable of detecting viruses. I know, crazy, but it had to be done, so we set about our task and designed a way to do that. First, we started with a magnetic bead coated in the streptavidin protein. Second, this thing is a biotin protein chained to the capture DNA, which is complementary partially to the virus DNA. Why did we use biotin, you say? And why streptavidin with magnetic beads? Well, biotin and streptavidin have a dissociation constant of 10 to the negative 14. That's right, 10 to the negative 14. So, once they bind, they don't ever come apart. The third object. This is our target virus DNA, which is complementary to the capture DNA. And finally, conjugate DNA, containing the enzyme DNA invertase, which is capable of enzymatically converting sucrose into glucose. Once we have glucose, we use our patented glucose meter here to detect how much glucose was in the sample and then determine how much virus DNA there was. Now, I'm going to turn it over to my esteemed colleague, Aram, who is going to explain how this procedure could possibly save thousands of lives every single year. No pressure.
Designing a once-in-a-lifetime experiment like this was an interesting challenge, but also one that could make us all potentially very, very rich. So this is what the procedure goes like. First of all, we have to make the conjugate DNA complex, which has DNA invertase and thiol DNA. So we basically mix two solutions, one of thiol DNA and one of DNA invertase, and allow them to conjugate. The next step is to bind the capture DNA to the magnetic bead. So again, we mix two solutions, one of capture DNA and one of magnetic beads. And then we separate magnetic beads bound to the captured DNA using a magnet from the solution. And finally, we work with our target DNA. So we mix the solution of magnetic beads and captured DNA with the target DNA solution. And here, the captured DNA will bind to the 5' half of the target DNA. We then add the solution of conjugate DNA to the complex that we already built. And this part will bind to the 3' half of the target DNA. And now our complex is complete. So we add a solution of sucrose. And our DNA invertase will convert the sucrose into glucose. And here is when we use our product. A personal glucose meter to detect the glucose that has been formed from sucrose.
Wow. But I assume at some point we had to actually test our results, right?
Of course. And to prove that this miracle device works, we turn it over to our crack team of researchers.
Okay, let's see what our crack team of hotshot researchers are up to.
Hi, I'm Dr. Xiang.
And I'm Dr. Li.
And we're FutureTech's crack team of hotshot super scientists.
Unfortunately, being super scientists, we have little time for small talk.
So here's how our research went. So in our research, we investigated the detection of 12-mer model DNA. We ran some trials in the absence of model DNA that produced negligible readouts in the PGMs. So then we ran some more trials using 10 nanomolar target DNA, and this produced a 40-fold glucose signal. Let me show you my results over here on my graph. Okay, so we graphed the results in a glucose meter signal versus concentration graph. As you can see, as the concentration increases across the x-axis, the signal increases as well, going up the y-axis. Under our experimental conditions, we found the detection limit to be approximately 50 picomolar DNA. Due to the large surface area of magnetic beads for DNA hybridization, the capacity of DNA binding was large, and the dynamic range was 0.1 to 10 nanomolar target DNA. Any samples with higher concentration produced a signal that was beyond the detection limit, so we excluded those from our calibration limit. Now, to evaluate selectivity, we ran the experiment again, this time using DNA molecules with 1 or 2 mismatches. And we found that there was little glucose signal, and this therefore shows this excellent selectivity of our method. So in our experiment, the glucose was produced via enzymatic hydrolysis by the invertase conjugates. We added sucrose in excess to magnetic beads containing DNA invertase conjugates to maximize the reaction time. The kinetics of glucose production should be dependent on the invertase conjugate concentration and thus the target DNA concentration. The more target DNA concentration in the solution, the earlier the sample showed a detectable signal over a month. Now, to ensure that low concentration of DNA was also detected, we allotted a 16-hour reaction time.
To demonstrate the versatility of the portable glucose meter, the enzymatic hydrolysis method was used to quantify a 35 nucleotide hepatitis B virus, also known as an HBV, DNA fragment using a portable glucose meter. The HBV fragment was obtained from the virus DNA by applying suitable endonucleases and other DNA cleaving reagents. Buffers of high ionic strength and magnetic beads of higher concentration were used to ensure efficient DNA hybridization and invertase loading. Long binding arms, high ionic strength, and more concentrated magnetic beads increase the concentration of target DNA and DNA invertase conjugates bound to the magnetic beads. This reduced the time for glucose production and increased the sensitivity. The number of base pairs for hybridization between the cap DNA and the target DNA was increased from 12 base pairs in the model DNA to 13 base pairs in the HBV DNA. The number of base pairs between the target DNA and DNA invertase was also increased from 19 base pairs to 20 base pairs in the HBV DNA. This was done to increase the binding affinity between the two strands. As can be seen from this graph, an 8-fold enhancement in glucose production can be achieved in the presence of a 50 nanomolar HBV DNA fragment. Samples that contained HBV DNA fragments of higher than 100 nanomolars produced glucose signals beyond the upper limit of the PGM, which was 40 picomolar, and therefore were not included in the calibration curve. The sensitivity of the PGM was comparable or even better than that of some other methods of DNA detection. It is also suitable for analysis of samples with high HBV DNA concentrations. The sensitivity can be improved by increasing the efficiency of pre-concentrating effect of capturing magnetic beads. The sensitivity can also be improved by increasing the time of enzymatic amplification for lower DNA concentrations. As can be seen from the graph here, a single mismatch in the HBV DNA fragment produces a modest signal by the portable glucose meter. However, under the same conditions, a fully matched HBV DNA fragment produces a much larger signal by the portable glucose meter. So there you have it. Those are the results of this experiment. So you're welcome, universe.
Well, I don't know about you, Jason, but I'm ready to buy as many of these puppies as my wallet can afford.
Absolutely. And operators are standing by right now.
Thanks to this machine here, I now know that I have hepatitis.
Are you serious? That fast? That fast? This thing's amazing!
Waiting for my herpes test to come back would take forever, but now it's quick.
And if you call in the next 30 minutes, we'll send you our new advanced PGM. Not only does it have all the features of our regular model, but it's also a beer bottle opener. Order your own DNA detecting glucose meter for only $299.99. Call now, 1-800-2400-8668. That number again, 1-800-2400-8668. Act now.